Many of the types of data that we've worked with so far in Python have actually been objects. Some people argue that everything in Python is in fact an object, but typically it's most useful to think about that the more complex types of data are represented by objects. Examples of this would be lists, our file handlers, even strings, things that we can call functions on with the dot operator, which we've seen before, but we'll see again in a moment, and things which have data and behavior combined together. Let's take a little bit of a deeper look at this concept. So we want to ask our data to do things. For instance, when I have a list, 2531, and I want that list to add another element to itself. I want 4 to be added on at the end of that. How have you seen that done before? If it's called my list and you wanted to have 4 added on at the end and actually change the variable my list, the list that it points to have something different, then what you do is you call the append function. So you say mylist.append, and then you tell it, what do you want to append? Oh, I want to append the number 4. Similarly, if I have a string and I want to ask that string if it is made up entirely of alphabetical characters, then think about how you ask it to do that, how you ask it to tell you that. This one is called myString, and its value that it points to is hello4. So in this case, we know that it will come back telling us, no, it's not entirely made of alphabetical characters, but how we ask it that is myString.isAlpha. And so again, this is calling a function, but it's calling it in reference to or from some object, some data that currently is called myString. That's just the variable name, but essentially what we're saying is whatever myString means, like the string hello4, ask that string, are you made of alphabetical characters? And in this case, when we get a result from that, it will be either true or false. So objects are a special data type. They can know things and they can do things. For instance, numbers are usually not considered objects because they only really know what they are. We don't typically call functions from numbers like 1 dot is even or something like that. We might write an is even function that operates on numbers, but we don't typically call functions from them because numbers really only kind of know their value. They can't do things themselves. You have to write a separate function that will do things to them or with them. When we're using an object, we use the dot operator to ask an object for something it knows or to ask it to do something. And as we just saw, we've done this before. This is a thing that we've done with lists. It's a thing we've done with strings. It's a thing we've done with file handlers. And so here, what we are essentially doing is we're asking mylist, the object that's called mylist, to append the number 7 to itself. And this changes it. Here are a few different examples of functions, and they're noteworthy because they're kind of different types of functions that objects could have. Objects can have a type of function called a mutator. This changes the object itself. Whereas saying 3 plus 3 or x plus y, that doesn't change 3 or it doesn't change x or y. So that's not a mutator. That's an operator, a mathematical operator. But a mutator is a function that you can call with an object and it changes the original object itself. This would cause my list to be 14627. On the other hand, there are other functions that we can call with objects that ask the object for something or ask the object to do something, but don't change the original underlying object. You may remember that I've said before that strings are immutable, in fact, and therefore they have no mutators. We can't tell my string to change itself to be uppercase, but we can ask my string, could you please give me a version of yourself that is uppercase? And that's what we're doing here. This generates a new object, but it does not change the word hello. It will give us an all uppercase copy of hello, but it doesn't change my string and the fact that that string is the lowercase word hello. So that's another type of function. Mutators change. There are functions that ask for information or ask for a new object to be generated, like the string functions, upper, lower, things like that. And then there are other functions that do something and maybe give us some new data. So here we have my file handler. We've opened a file and it's pointing to that file. It's handling that file. When we say read, that asks the object to give us some new information. It reads the contents of the file. It's also worth noting that read is sort of also a mutator because while it doesn't change the contents of the file, it changes where the file handler is looking. For instance, when I do read line, that changes the file handler to be looking at the next line and the next line and so on every time I say read line. So it's sort of a mix. Some functions are a mix of this mutator idea and this idea of a function that generates something new, some new value to give us. Read gets data from the object, data from the file that the object is handling, is pointing to and reading through, and it changes the location that the file handler is pointing to at the same time. So there's a wide range of types of functions that objects can have, but it's important to understand that those functions, when executed, are always doing things in reference to the object itself. For instance, when I say mylist.append, it knows who it's appending data to because my list is on the left-hand side of that dot. So that tells it, append, oh, what am I appending to? I'm appending to my list. We don't have to provide it as a parameter to append because we've called append from that list object. And the same for mystring.upper. It's not confused about who it's uppercasing because we've called it using mystring. Mystring is the object in question there, and so on for the file handler. We've used objects already, whether you knew it or not, and will continue to do so. But we can also create our own object types. What we do is we give them a specification, and that specification is called a class. So the specification tells the concept of what that type of object might look like. Just like we know strings as a general concept, strings are some sequence of characters. That's what the string class specifies. It says, well, you're going to have a sequence of characters. And people can ask you if those characters are uppercase. They can ask you to find something inside of that sequence of characters and so on. That's the general behavior and data that it has. That's what the class specifies. Then we create actual instances that are the objects. The word hello stored as a string, that's an object. So you can think about these as like the class is a category, and that category specifies what kind of data will belong to that type of object and what kind of behavior will be available to all objects of that category, of that type. And this can be a little difficult for people to understand when they first begin programming with objects and classes, because you've got to think in a very abstract way when you're defining a class. Well, what's possible for a string to do? Or in the example we'll look at, what's possible to know about a student? And we don't always encapsulate everything that's possible to know about that student, but what's important to know about a student? Well, we at least want to know their name and their email and maybe a list of classes taken. And so here we're giving a general specification that, well, a student will have a name, an email, and some classes that they are taking or have taken in the past. And that's what the class specifies. It doesn't tell you what the name of a particular student is. It says students have names, and students have emails, and students take classes, and we'll keep a list of those. Then we think about what can we do with a student, or what can student objects do? Well, we might want to be able to print out their email address so that we could email all the students in a particular class. We might want to be able to add classes, drop classes, things like that. And we might want to be able to get the full transcript of all of the classes that they have taken. And these would be specified as functions. They're functions that belong to the student class. They can't be called unless you have a student to call them with, just the same way that isUpper can't be called unless I have a string to call it from. So I'm going to need to specify a specific student. We do that by calling a special function that has the same name as the class. This is also sometimes called a constructor. So here we see that we're creating a student variable, and we say it equals student, parentheses. That's calling a function that creates a new object of that type. In this example, we haven't given it any parameters. We will eventually see how we can give it some parameters so that we could specify the student's name and email and classes taken and things like that. Because this would be a little silly, because right after we create the student, we ask for their transcript. Well, it won't know their transcript yet. So this is just a very straightforward one that would either give you like an empty list for the transcript or might have some default transcript. All students take blah, or that kind of thing. But the most important thing to take away right now is that a class gives the specification. What's possible? What's it possible to know about a student, and what's it possible to do with or for a student? What is it possible for a student object to do? And then the example down below just shows a very, very simple, well, we can create a student object, and that's one specific student. Ideally, that student will have a name and an email and classes taken that we could specify, and we'll see more about that in a moment. But once we have a student object, we can call any of these functions. Now, this design that I've laid out here would have to be written in actual code. You will have to specify that a student is a class and that it can print the address, it can add a class, it can get the transcript, and specify the kinds of data that it has as well. We come up with the design for classes first so that we know what objects of that type will look like, what data will they have, and what functions or what methods will be associated with them. When we come up with the design for a class, we want to try to keep to an idea of encapsulation. There should be boundaries around what that idea means and what's important to know about it. Here's an example. If I were writing a car class, I would probably want to know things like the make, model, and year of that car, maybe the mileage that it has on it, some other things about the car's particular details. What I don't need to store with that car is the current stock trading price of the company that creates that car, or the speed limit of where that car is currently located, or things like that. Those might belong to, say, a company class for the stock value of that company. Those might be well associated with a road so that if I were planning routes for that car, I would be able to go from road to road and know the speed limits there. But we want to encapsulate in the car class only the things that make sense to be specific to one exact car. I wouldn't write down, along with information about my car, those other things that I mentioned. I would only write down the make, model, year, license number, things like that. We usually, when we're designing a class, we choose some noun, because nouns represent objects, we choose some noun that might exist in the real world or might exist for the application that we are trying to do. So a stock might be a reasonable thing to use as a class concept. It's a noun. It may not be a physical object, but it's an object in conceptual terms that we use in the real world in finance and to make decisions and to store data, and to associate with particular data and behavior. A stock has a price. That price can go up. It can go down. It can have a certain number of shares associated with it, or that kind of thing. So we choose some noun to represent either a real-world object or some conceptual object that people will use in the application domain that we're thinking in. Bikes or cars or employees or students. And then the class, as I've mentioned, is a blueprint for what's possible. And then we create specific objects by filling in the data related to that class. We talk about cars as a general thing. Well, cars have a make, model, year, license plate number, number of miles driven. That's the class. And then the object would be my car, that it is a 1992 Prius with, it's not actually, but you get the idea that I fill in the blanks of those different data pieces, and now I have an object. It's that one specific one. So again, string is a class. The actual string, hello, Hello, that sequence of characters is an object. The type, when we talk about types, is the same as the class. Its data type is string. So each object has a type associated with it. That type is the class that was used as a template to create it. Strings are a little bit of a funny object because we don't call to a constructor typically to make a string. We just write in quotes and get a string object. Similar for lists, we can actually call to a list constructor and create an empty list that way, but we usually don't. We usually define it in brackets. The student class and other classes that we define will not be able to be written as literals like that. We will have to call to a constructor, like the example we saw before where we said student, parentheses, and that creates a new student object. You can actually do that for strings and for lists, but we don't do that as often. So here's a more detailed example of student, and it has actually some code with it. This is based a little on the design before, but you can see that it actually has a different function, for instance, than what we had before. So the most important part to start off a class is that you have to use the keyword class and then give the name of the class. Typically, we use uppercase as the first letter for a class so that it's clear that it's different than just a variable that represented a student. And so here we've defined that constructor, or initializer is another. In Python it's called init, and it initializes. It creates that object with the specific details that we need for that type of object. So here this student has an ID number and a name. We're not going to give them the class list and all of the other stuff and the email and things. For now, let's stay simple. They'll have an ID number and they'll have a name. So this is a different specification than the one that was shown before to keep it simpler. And probably for a realistic use, we would want more information like that list of classes. So we define this constructor, this initializer. It has some parameters. Two of them might make sense to you, the ID number and the name. We also have to tell it self. In Python, this is what gets filled in by whatever was left of the dot. When we say like my string dot upper, that's self inside of the function. It's sort of an invisible parameter when you call it, but when you write the function, you include that parameter to say, I want to have a handle on the object that was used to call this. So here, then inside, we can say, well, this object itself should have an ID number. And I'll set that ID number to the one that was passed in as a parameter. And this object itself should have a name. And that name will be the student name that was given as a parameter there. That stores them. And it stores them in the scope of this class, of this object rather. So it means that this specific object is attached to whatever ID number was given and whatever name was given. You can then refer back to those in other functions. So it's a special new scope, not like the local scope we've used a lot of the time in functions, and a little different than the global scope that we talked about briefly. But this is a scope that's specific to the object itself. So that when I call display, for instance, I have a reference to the ID number because I can say, whoever the object is that display was called with, then get that one's ID. And whoever the object is that display was called with, get that one's name. These must match the ones that were used to define those up above, usually in the initializer, in the constructor. There are special functions in Python that start and end with 2 underscores. You've seen a similar thing to this when we wrote main sections of our standalone Python programs before. Whenever Python has some special value that it kind of wants to reserve, that you should never be able to replace, it uses these underscores here to indicate like, hey, this is really special. Take extra care with it, like the main or the name being equal to main, or things like that. The underscores indicate that it's some special thing. And you'll notice we don't call init here. We use student. So the underscores do some indicating that this should actually be associated with the student class. This is how I build a new student object. You'll see many more of those if you do more Python programming further down the line. Then we can define other types of methods. So the initializer, the constructor, is just a method, but it's a special method. We indicate that by these underscores there. The display method is sort of just more a standard method. Method and function are words that I'll sometimes use interchangeably, but usually method indicates that it belongs to a class. Standalone functions that don't have to be like string dot something, those we often just call functions, and then the ones that are associated with a class, we'll call them methods. So this one is just a plain method. It's called display. We can give it any name we'd like to. We do have to make sure that it has self as one of its parameters, so that I can ask about the ID number or the name, or in the case of like a string class, I could ask about what the first character is, or all of the characters, or different things like that. It helps us to reference the data about this object. So down here, we see we've created a student as a variable. We've set it equal to a new student with the ID 4 and the name Bob. So that creates that new object and makes the aStudent variable reference it. Similar to how when we call open, that creates a new file handler object and gives us the ability to read from that file or write to that file or whatever we're able to do. So then once I have that object, the student whose ID is 4 and name is Bob, then I can do things like call display with it, aStudent.display. That feeds in that student object as self into display so that it would print out 4 and Bob as the result from the display method. Here is another class example. It is dice. It's going to do some random generating of a particular value. These dice can have their own value set that is what they will actually roll. So a 6-sided die or a 10-sided die or those sorts of things. Oh, my apologies. It's not actually what it rolls. It's how many rolls it does. So how many dice to roll. But you could specify a die class that takes a number and that is the limit of what it can roll, 1 through 6 or that kind of thing. Here, however, we create an empty list and then we're just going to roll dice, 6-sided dice, however many times was specified in the constructor. And then we're going to be able to display all of the results from rolling those 6-sided dice, however many times was specified. So similarly, we've got a constructor or an initializer. It has the name init with the underscores. That's absolutely required for your constructor or your initializer. Same word, just different people call them different things. And then it has a method, also called display here, but again, it could be called anything. It could be called print results or print rolls or something like that if you wanted to. It takes just self, whereas the initializer here takes n, and then it generates a list of dice rolls up to n of those rolls, or always n of those rolls. And when we print here, we're going to end up printing out just that list of the results of doing n dice rolls. And so here we have a variable, my dice. It's equal to dice with 2, because remember, we don't have to provide self. Self is kind of automatic, especially in the constructor, the initializer. We do have to provide the n. So this is saying roll 2 dice. So it will generate a list with 2 random dice rolls in it. Then when we call display, you'll notice we're calling it with my dice. So that will take that object that was just created, that object that has a list of 2 dice rolls, and it will display those dice rolls, the list containing the results of those dice rolls. If I called display 5 different times, it will display the same 2 numbers. They were randomly generated when the initializer was called. They will not change based on being displayed. If I created a new dice object, I said dice 2 again, and then asked to display that one, those would possibly be different rolls because they would be 2 different random rolls. So the randomization and the creation of this list only happens in the initializer. The display, you can see right here, it does nothing else but printing out. So anything that you save inside of the initializer or inside of a particular method from a class, it will stay saved until some line of code inside of the class tells it to change again. Well, or outside of the class, but that gets much more complicated, and we don't want to deal with that right now. We may look at that here soon. So many of the things that you've worked with so far are objects. They're complex data types that they need to have both memory of what they are, what data they have, and methods that allow them to do particular behavior. Strings know that they have certain sets of characters, and they know how to make those characters all uppercase or check if they're all alphanumeric or different things like that. And then we can create our own objects by first designing a class that encapsulates some idea, like a student, like a car, like a set of dice rolls. And we then define that class with code. Typically, we'll provide an initializer or a constructor that allows us to specify the data that's needed for that class, for that object, like a student ID and that particular student's name, like Bob. Then, once we've created that initializer, we can work on methods that allow us to change the data of the object, mutators, like the append method for lists that actually changes the underlying list. We can create methods that give us data about the object, like isUpper, or things that will check things about a string. We can create methods that give us new information or new copies of the object. For instance, upper, which creates an uppercase copy of the string that it was called with. Once we've specified the class details, which are sort of a blueprint or a template for what the objects are allowed to look like and do, then we actually call to the initializer with the correct values, if it takes any values, and that gives us an actual concrete object that has a name or an ID number or a set of dice roll values. And from there, we can call the methods of the object and do many things with them.